Hello everyone, welcome to the control system. This is part 3 of lecture 7, Transient and Steady State Response Analysis. In this section, we'll discuss second order system. Okay, so in this section, we shall obtain the response of a typical second order system uh, to this step function, unit step input, ramp input, and impulse input. So let's consider the servo system. So the servo system consists of proportional control, K, and there is no S here, and load elements, inertia, and this is an inertia, and viscous frictions, okay, damper. So suppose that we wish to control the output C, okay, the output position C in accordance with the input position R. So the equation for the load element is this. J is the inertia. C dot dot is a second derivative of position. B is a damper. C dot is the first derivative of position. And T is the torque produced by the proportional controllers, K. Okay, this is in time domain, so we want to transform from time domain to S domain. So you need to take the Laplace transform from both sides and assume zero initial condition. You will obtain these equations. And then we'll do a little bit of manipulations. You will obtain this transfer function, Cs over Ts. So by using these transfer functions, can you find Cs over Rs? Can you? Or you can use this block diagram. Well, please try. Please try maybe 10 minutes. And then after 10 minutes, you can come back to the class. Alright, let's continue. So this is the block diagram A, and then from this block diagram you can obtain this. This is what we did in the previous slide. Okay, ratio between Cs over Ts, and then you need to combine these two blocks. Okay, if you don't remember how to do this, go back to lecture 5 on block diagram. Combine this block, you will obtain this one. And then you need to combine between this block and this block. Okay, and then you can find the ratio between Cs over Os given by this. So the first equation can be rewritten as this one. And the system like this have two poles. The pole is the root of S. Okay, so the pole is the root of S in the denominator. This called second order system, S squared. Okay, now the closed loop transfer function of the system can be found like this. Alright, and then which can also be written as this. So the closed loop pole complex conjugate is the delta b squared minus 4jk less than 0, and they are real if this larger than or equal to 0. Okay, so in transient response analysis, it is convenient to write j over s equal omega n squared, b over j equal to psi omega n equal to sigma, where sigma is called attenuations and omega n is called undamped natural frequency. Psi is called damping ratio of the system, and the damping ratio psi is the ratio of the actual damping B to the critical damping BC given by these equations. So in terms of psi and omega, the system C can be modified to a generic form, which is given by this, alright, in terms of omega n and psi's. So when the closed loop system given equation 10 can be rewritten as this. So this is called the standard form of a second order system. So the behavior of this system is only depend on this omega n and psi. Okay. All right. Next, so let's move to the case if 0 less than psi less than 1, the closed loop pole are complex conjugates, and it lie in the left half planes. So the system is called undamped. Okay, and the transient response is oscillatory. And if psi equal to 0, the transient response does not die out. If equal to 1, the system is called critically damped. If it is larger than 1, the system is overdamped. Alright? So we shall now solve the response of the system, this, shown below, like this. Okay, now consider undamped case with 0 less than psi less than 1. So in this case, Cs over Rs can be written like this, where omega n given like this, and this is called damped natural frequency. This omega d is called damped natural frequency. So for the unit step input Cs can be written like this. And do a little bit of math. Take the inverse Laplace transform. I mean before taking the inverse Laplace transform, we need to rewrite this Cs in this form, and then we can take the inverse Laplace. This is a good property that we should use. And then the inverse Laplace transform Cs can be obtained. This is Ct in time domain. Can be also written in this form as well. So it can be seen that the frequency of transient oscillation is the damped natural frequency omega d, and thus vary with damping ratio, this one and this one. Okay, and then you can find the errors. The error is just RT minus Cs, and this one is an errors. So the error exhibits a damping sinusoidal oscillation. This sinusoid goes sin and sinusoid. So at the steady state, it means that t equal infinity. It go to infinity. T is very large, and there is no error exists because of this term. Okay, will go to 0. So there is no errors when t is large enough. And if this equal to 0, and then Ct will only equal this one. Okay? I mean when this equal to 0. This term will be gone, and only this remain, 1 minus cos omega and t. Okay. In the case of critically damped, C equal 1, if the two pole of Cs over Rs are equal, the system is said to be critically damped. So for the unit step input Rs equal 1 over S, Cs can be written like this. You take the inverse Laplace transform, you can find Ct in time domain. And in the case of overdamped, where Ct, where psi larger than 1, in this case, the two pole of Cs over Rs are negative real part and unequal, or the unit step input 1 over S and CS can be found like this. And we'll do the same process. You can find CT in time domain. So when psi is appreciably greater than unity, one of two decaying exponential increase much faster than the other. So the faster decaying exponential term may be neglected. It means that this is much greater than S1. Then for an approximate solution, we may neglect S1. This is permissible because the effect of S1 on the response is much smaller than S2. So since the term involve S1 decay much faster than the term involving S2. Okay, so when the faster decaying exponential term has disappeared, the response is similar to that of the first order system, which is this. Okay, so with an appropriate transfer function Cs over Rs, the unit step response can be obtained like this. And the time response Ct is then can be found. So this gives an approximate unit step response when one of the pole of Cs over S can be neglected.